Hello, everyone. Thank you for being here. We have a second attempt for Jeremias Knoblauch, who's going to talk about optimization-centric generalization of Bayesian inference. So please go ahead when you're ready.
Okay, thanks for giving me a second chance. So I already said I've connected the Ethernet cable into the laptop this time. So let's hope that the Wi-Fi doesn't die on us. Thanks for being here. It's a pleasure to be back. And what I want to talk about is sort of a very broad survey / overview over some of the things I've worked on over the past years. And so I won't go into too much detail on any of the particular things I'm touching on. If any of those interest you, you can get in touch directly, or I think there's also references to some of the particular papers that I'm referring to on the slides. But yeah, I'm always very happy to discuss things in more detail. I just don't think it's the most interesting thing to do on a Friday afternoon, maybe. Okay, so the big takeaway that I would like you to get from today. Oh, and by the way, if there are questions at any point, please just interrupt me. Like, no need to raise hands or whatever. I don't know how it's usually handled, but feel free to just jump in and hijack the presentation. What I would like you to take away from today is essentially the message encoded in this picture here. When you do Bayesian inference, you're essentially solving a particular type of optimization problem. But the space of optimization problems you could be considering is much larger, and so the question arises, why are you dealing with this one particular optimization problem? It turns out that this one particular optimization problem, Bayesian inference, makes a lot of sense under particular assumptions, but when these assumptions aren't met, it's sort of doubtful whether you should really solve this one particular problem. And then in particular contexts, namely in statistical machine learning, these assumptions will often be violated, and so the question imposes itself whether you should really be targeting this one specific problem. And today I'd like to argue that there are many other problems you should consider maybe, and that there are situations where it's indeed very beneficial for you to consider these alternative problems. So on a very abstract level, that's what my message will be today. And so the structure for this will be in 3 parts. So first, we're just establishing notation, we're going through Bayes rule again, and also linking Bayes rule to a particular variational problem, so an infinite dimensional optimization problem of the space of probability measures. And that's where we spend the second part on, which is we'll be talking about what this optimization problem looks like, why it's interesting for us to study this, and how we can maybe generalize this in a fairly natural way. We'll look at some special cases, and then we'll sort of look at how you can go beyond what people have done in generalizing this optimization logic. And I'll look very superficially at some of the ideas that we've explored with this over the last few years. Okay, so before we start, the obligatory picture of Thomas Bayes, even though it's not actually Thomas Bayes, and it's not actually Bayes' theorem, but it's actually the form of Bayes' theorem that you would find in Laplace's text, which comes about 10 years later. But just to set the stage for the notation we'll be using x to denote our observations here. N observations are collected in a vector x. The prior is always going to be denoted by pi, and unlike what most people would be using for the posterior, we'll be using qn, and we'll be using q star n because, as we shall see later, q star is actually the solution of an optimization problem. The likelihood terms, and more generally speaking, later on the losses, so the things you're trying to minimize or maximize in this case, will be colored in orange. And as you obviously all know, because this is what the department works on primarily, is Bayes rule looks like equation 1. You have a posterior which is obtained by updating your prior multiplicatively with your likelihood terms. And what this means is that you can interpret Bayes rule in the way that most of you will be familiar with as a belief update operation. So you start life with a prior belief, you interact with the world, you collect your likelihood terms, and then you use those to update your prior into a posterior belief about the state in the world in form of your Bayesian posterior. There's a problem with this. Actually, there are 3 succinct possible problems with this, and they relate directly to why one would compute Bayes rule to update a prior into a posterior. And one of them is you need to ensure that the prior you're starting with actually makes sense. So what this means is, well, first, let me backtrack. Actually, the very thing you need to start with is that your belief about the world can be perfectly encapsulated in some parameter. What this means in practice is, because your belief about the world will be usually specific to one particular data phenomenon, which we described with the vector x, what that means is that your beliefs about how x were generated have to be compressed into beliefs about one parameter theta that indexes the likelihood. What that means is your likelihood should be an accurate description of how the data were generated. Otherwise, you can't even formulate a prior belief about the world you're trying to interpret. Then, second step, you actually need to be able to somehow encode the prior beliefs you have about the true state of the world, aka your beliefs about theta, in a prior. So you need to be able to mathematically write down in precise form the full amount of all prior knowledge that you have about this parameter theta. And then the third part, which is a problem that a lot of you I know work on, is that you actually need to be able to compute that posterior. You need to be able to work with it. Otherwise, you can multiply terms together, but they won't be very useful in practice. They'll be a mathematical object. They won't be an object that's of interest in the real world. So these are the three assumptions that essentially underlie most of Bayesian inference in some form. And there's a problem with these three assumptions the moment you leave what I would call the traditional interpretation of statistical inference. And in this traditional interpretation, which is the one that we would get taught at university, is some domain expert approaches you with their data or their problem and says, "Dear statistician, please help me figure this out. Here is what I know about the problem. Now we need to formulate a likelihood model that encapsulates my prior knowledge about how the data were generated. And then I will tell you what the literature says about the parameters that appear in the model that we have formulated for the data. And then you and I will sit together and we'll condense them into some prior, basically prior elicitation, right? And so in this schematic, what comes first is the problem, then comes the likelihood model and the associated prior. And what happens then is inference. So once the statistical model and the prior is fixed, all you need to do is you need to find the best MCMC algorithm to compute the full Bayesian posterior. Your problem is essentially solved at step 2, right? I mean, that's an exaggeration, but the moment that your model and your prior are fixed, Bayesian computation is the best thing you can ever do. Now, in contemporary statistical practice, in particular in what people call machine learning, often the problem is actually formulated backwards. So rather than starting with data or a problem, people will come up with some algorithm or a statistical model for the purposes of this presentation. So you have a statistical model. That means a likelihood and a prior. And then you don't actually know what kind of data you will be encountering yet. And you're just trying to design an algorithm that is versatile enough so that it can deal with a wide range of data problems. And if you think that's an exaggeration, that's in fact exactly how, for example, deep Bayesian learning operates. So in deep Bayesian learning, you would use a neural network. Then you will have Bayesian beliefs about the weights in that network. And you would propose typically some priors and some network architectures before you actually see the data. So it is actually exactly how this functions. And the moment that these roles get reversed, it's quite clear that the assumptions that we made on the previous slide will no longer make sense, right? We do not have correct likelihoods because we're specifically trying to design the likelihoods to just be extremely flexible. So they're not parsimonious. They're probably over-parameterized. There's probably not one theta star, but possibly infinitely many theta stars. The prior that we have doesn't actually encode information anymore. If you're trying to impose a prior on a Bayesian neural network, you are saying that you have a good guess about likely weights of a parameter in a neural network in the third layer at the 68th node, which is fairly unlikely. And then you're also assuming that you can actually compute the entire thing in closed form, which is basically impossible in most machine learning applications. So you always need some form of approximation. Okay, so this is why we care about these three assumptions, because in a lot of statistical practice, they will be violated. And yes, this is just what I just said, written in text. And so once we've made that observation, there is one way we can go about trying to address this problem. And the way I will try to do this is by rewriting Bayesian inference as an optimization problem. So in the second part of the presentation, what I want to achieve is I want to get people to stop thinking about the Bayesian posterior like people commonly do, which is depicted here on the left, where you have distributions and you think about the Bayesian posterior as inherently related to distributions. And rather, I would like you, I mean, it's always going to be a distribution, but rather I would like you to think about it as the outcome of a possibly constrained regularized optimization problem. So that is the purpose of this section.
Jeremias, can I ask a question? So I'm a bit fascinated by your kind of terminology in terms of correct likelihoods. So what is really correct likelihood? Because if you have like a super flexible non-parametric model, then most probably what you are trying to do is to alleviate some of the stress from the learning stage, so the estimation stage, into a specification stage. And, you know, that's fine. So, you know, if you have like, let's say, a Dirac delta likelihood, right? This is always correct in a sense. So where do you draw the line?
So, I mean, this is obviously there's also people would argue. So I've simplified things here. So here I said there must exist a true theta star so that we recover the data generating process, which subjectivist Bayesians would even disagree with. I've just tried to simplify things. In essence, you always run into the same problem. But let's take your example of overparameterization, because I think it's an interesting one. Let's say we have multiple theta stars that actually work. Then the likelihood would be correct, but you haven't. What you've done is you've made the second problem more complicated, because now you need a prior belief that can actually deal with the overparameterized likelihood. So in practice, you can probably argue that neural networks would have well-specified likelihoods in the sense that they are probably capable of recovering many data generating processes. But you've just shifted the problem into the prior.
Yeah, into the learning stage. Yeah.
Yeah.
Okay.
Exactly.
Yeah, thank you.
Any other questions at this point? Cool. Okay. Right. So, like I said, we now want to try and tackle these problems with rewriting the Bayesian posterior as an optimization problem. And the nature of this optimization problem is depicted in equation 2, because it turns out that you can rewrite the Bayesian posterior as an optimization problem of the following form. You optimize over the space of all probability distributions on theta, and you optimize an objective of two competing terms. One of these terms is trying to stop you from deviating too far from your prior, and this is why this is a Kullback-Leibler divergence, which, if you want to know what it looks like, this is the definition of a Kullback-Leibler divergence between Q and pi. And essentially what this term does is it anchors you to pi. You're not allowed to deviate too far from what you believed before you saw any data, but at the same time, you're also trying to minimize this first term here, which is the expected loss that you incur. And loss here is defined in terms of the negative log likelihood. And if you rewrite this, actually, the proof that this is exactly equal to the Bayesian posterior is surprisingly easy. All you need to do is you need to observe that you can actually rewrite this entire expression as a Kullback-Leibler divergence between Q and this term here. And then, because the Kullback-Leibler divergence is uniquely minimized if both arguments are the same, you have the result. Okay, so this is what we always do. When we compute Bayesian posterior, we're solving a regularized loss minimization problem. So I'm thinking here about the loss, and I'm thinking here about the regularizer. And this is a second interpretation that is complementary to the one we saw earlier, which was the one we're usually familiar with, which is the updating of a prior into a posterior. And so we have an updating interpretation, but now we also have an optimization interpretation. Okay, and so the moment we see this, there are some very natural things we can think about given the problems we've just explored. So, like we said, one of the problems we have is that our likelihoods may be misspecified, right? So let's take the opposite case of what we were discussing earlier with Ioannis. So rather than having a likelihood that is expressive enough that there actually does exist a true theta star, let's assume that actually we have been a bit too stingy with our likelihood, right? So we won't be able to recover the true data generating process for any theta, and maybe our likelihood specification is pretty poor, so we'll always be quite far away. In that case, actually using the log likelihood gives you a lot of problems, because the log is not a particularly robust, what's called scoring rule. It's called a scoring rule because it scores your model with respect to the data. So what you may consider is using a different scoring rule for the model and just plugging it into this part of the optimization problem instead. And that would protect you against certain forms of misspecification. So for example, outliers are a good example where changing the scoring rule here would protect you against doing terrible things with your Bayesian posterior. What I mean by that is that your Bayesian posterior, when there are lots of outliers, it might shift towards the outliers if you use the log likelihood scoring rule. But if you use another scoring rule, you may prevent that behavior. Similarly, we saw that the priors may not, in fact, be priors in the traditional sense, but they're more like reference measures. So they're not really encoding any useful beliefs. So you may want to weaken the regularizer, because actually the Kullback-Leibler divergence is a relatively strong regularization penalty. So it'll be really strict about deviating from the prior. So if your priors are pretty weak, you may want to weaken your regularizer so that the entire optimization problem reacts more to what the data does rather than to what you believed before you saw the data. And lastly, the last problem we saw right at the beginning was that your computing power may be insufficient to actually compute the Bayesian posterior in its entirety. So what you may want to change is actually the space over which you solve this objective. And in fact, this is what people call variational inference, even though it's usually motivated in a different way. So usually when people explain variational inference, they will talk about it as minimizing a pseudo distance between the true Bayesian posterior and a parameterized set of distributions. But actually, it turns out it's equivalent to considering the Bayesian optimization problem that you always solve when you compute the Bayesian posterior, and then actually just solving it over a subset over what you considered in the original formulation. Okay, and this leads you very naturally to the following generalization with 3 arguments, each of which can address one of the problems that we pointed out earlier. So here, rather than now only considering the negative log likelihood, the Kullback-Leibler divergence, and the space of all probability measures on theta, we've just replaced the 3 arguments from before with pi, which may be any subset of p theta, with the orange L, which may be any loss function that couples a data point xi to a parameter theta. And in particular, this loss need not even be model specific. So for example, you could imagine trying to find the median of a sample that you have collected. And a natural loss to use for the median would just be the absolute difference between theta and xi. In that case, theta would just be a median. You could have a prior belief about the median, and you could try to infer a posterior belief distribution about the median. And the third part being the way that you regularize against your prior beliefs. And sometimes I will call this the rule of 3, and I will abbreviate it with this notation here. So this triplet notation that basically just tells you any posterior of this form will consist in 3 arguments and looks like this. It's just a notational shorthand. Okay, now it's all fine and good to generalize things, but is it actually useful? And here on this slide, I sort of want to convince you that it's useful because these objects are already being considered in various contexts, and all we're doing is taking another logical step towards making it even more general, so it can encompass things in a natural way. So the case we're all very familiar with, obviously, is the standard Bayesian case. We choose a particular loss function, the negative log likelihood. You choose the Kullback-Leibler divergence, and you choose the set of all probability measures. Then if you have computational considerations and you may want to approximate that posterior, you can do variation inference, as I alluded to earlier, that actually amounts to just doing the exact same thing, but over a subset of probability measures. So this downward arrow here indicates that you're now considering only a subset of the original space to optimize the problem over. But actually, there's a lot of literature on considering what are sometimes called Gibbs posteriors or quasi-posteriors, pseudo-posteriors. They have many names, also pack Bayesian posteriors. And these kind of posteriors, they will just replace the negative log likelihood with any loss function. Also sometimes called exponentially weighted aggregation, because the form they take is you have the exponential of minus your loss function times the prior divided by the integral over the same thing. And here again, you can do the same thing. You can say, maybe it's too expensive for me to compute the entire thing. Let's just consider a subset and then optimize the same problem over that. And that once again gives you the variational approximation to these posteriors. And then what we essentially have done with what I've showed you now is we've just added another layer where we can also change the third argument now. We can also change the divergence. And the case where we've changed the divergence and the space and the loss or where we've changed one of them, you could encompass that entire thing by calling it a generalized variational inference posterior, because you've now given yourself the freedom to subjectively change the 3 arguments in your problem to address the 3 practical concerns that may arise using standard Bayesian methodology in the machine learning context. Okay, so just to clarify terminology, just so that it's not confusing, and the rule of 3 is the abstract generalization that I've put on this slide. When I speak about generalized variational inference, I speak about this particular subcase, and that's the subcase that we can actually solve, because I can write down these problems and they look nice, but unless this term here somehow ensures that I can actually solve this problem in a practical manner on some real data problem, it's not immediately useful. And while we'll see later that there are some cases where we can still optimize over the entire space and obtain a closed form for the solution, that's actually not typical. So usually you will be forced into using a subset of parameterized measures on theta if you actually want to tackle this problem. So with that, when I use the word generalized variational inference, I mean a case that we can actually solve. So it'll refer to the methodology rather than the abstraction that I've just presented. Okay, and in the next part, I'll go over some examples where we've applied this logic of generalized variational inference or the rule of 3 to actually contribute methodologically to a couple of places. So one of those examples that we did fairly early on was change point detection when you're observing a time series online, but then you also have outliers that might fool your algorithm into believing that an outlier actually it marks the beginning of a new segment. So you would detect a change point even though actually it was just a one-off outlier. Then very recently, we've looked at using the total variation distance for discrete outcome modeling. So when your loss function is changed from the negative log likelihood to the total variation distance, I'll look at some tractability issues and at 2 cases for Bayesian deep learning. Before we do that, it makes sense to sort of recapitulate one thing, and that's that when you are doing the standard Bayesian, when you're computing the standard Bayesian posterior, you are effectively using the Kullback-Leibler divergence twice, once for the prior and once for the model term. And the way to see this is just rewriting the loss term in terms of the Kullback-Leibler divergence. So it's fairly easy to, I haven't done anything magical here. I've added a term and subtracted a term that doesn't depend on theta, so I can always do that. It's just a constant. And what turns out to be the case is that I'm essentially, I'm downweighting the prior at a rate 1 over n. I'm downweighting the Kullback-Leibler divergence between the prior and the posterior with 1 over n, while computing the Kullback-Leibler divergence that I get empirically from the data and the model that I've posed. And then one obvious question would be, what kind of disadvantages do I have from minimizing the Kullback-Leibler divergence between my true data generating process and the model I've posed? And the general answer is, if your model is correct, the Kullback-Leibler divergence is the most efficient way of extracting information. And you can actually see this in a lot of mathematical results. So for example, you all know that the maximum likelihood estimator will be asymptotically the most efficient one under certain regularity conditions if the model is correct. And this is because doing maximum likelihood is essentially the same as using the Kullback-Leibler divergence. But the moment that your model is inappropriately specified, you may want to use a different divergence here, and that would result in a different scoring rule. So a lot of the examples we'll be looking at essentially just leverage that insight, where you replace the divergence or the discrepancy measure that you use to say how close the truth that you've observed is to the model. And one thing that we did on that front fairly recently is actually look at the total variation distance. It has complications doing this, because unlike the Kullback-Leibler divergence, which you can see here is nicely additive, the total variation distance won't be additive in your data points anymore. So there's some complications that come with this. But one thing that the total variation distance is very nice for is robustness. And one way you can see this immediately is that the total variation distance is bounded, and so is its influence function. So if you plug that into a Bayesian formalism, you inherit the properties that you would get from Frequentist estimation. And here are just some plots that essentially show you what happens in a zero inflation model. So if you have a Poisson model, but you have zero inflation, but you're unaware of the zero inflation, so you don't account for it in the model, and you're just fitting a standard Poisson model. The question is, how big is the absolute difference between the true parameter of your Poisson model and the one that that you get using your Bayesian posterior? And here on the left-hand side, for example, we plot what happens if you use the standard Bayesian posterior versus you use the total variation distance. And what you can essentially see is there will be some pollution that the total variation distance also suffers, but once it reaches a certain level, it won't get fooled into becoming worse and worse and worse the more zero inflation you get. So this is something you can do. Another thing that I mentioned was the change point detection problem. So here is an example of what the algorithm, the vanilla algorithm, which is called Bayesian online change point detection. Essentially what it is a recursively updated Bayesian posterior about change point locations. What that change point posterior actually looks like on a multi-dimensional data set. So here it has 5 dimensions. So it's a 5-dimensional time series with joint change points. The joint change points fairly easily to disentangle from this plot. It's here and it's here where the dynamics change. So these are the true change points, but actually there are also outliers in here. Now the nice thing is, because this happens in 5 dimensions, you actually don't see these outliers, and I don't see these outliers. I've once tried to identify them visually, and I failed quite spectacularly. So there are outliers in here, but you wouldn't know. So you would still think that the model you've posed is a decent description, but it really throws your inference algorithm off. And so all the red lines you see here are incorrectly determined change points that the algorithm insists are there, even though they're not. And this is a result of outliers. Now what you can do is, once again, change the loss function or the way you score the model, and you actually get this picture instead. So this is something we did in 2018. Where we used what's called the beta divergence. Sometimes it's also called the, it has a second name. Okay, sorry, I forgot the second name. Density power divergence. It's also called density power divergence. And you can use this and you can tune the parameter beta in such a way that actually this becomes robust. And then you can perform the same inference scheme as before, except now rather than tackling the exact Bayesian posterior, what you are tackling is this generalized Bayesian posterior, and that then informs which change points you declare. And here you can see that the change points posterior looks exactly what we would like it to look like. At the moment, I'm also involved in working on using this for intractable likelihoods. So intractable likelihoods are likelihoods where the normalization constant cannot be computed in closed form. So you know the likelihood, but only up to a normalization constant. And this can sometimes cause you problems in actually computing the Bayesian posterior, because the procedure essentially requires you to estimate 2 integrals. So you introduce complications. And one question we were asking ourselves is, can we eliminate at least one of those problems? And the answer is actually yes, because there's a suite of methods in frequentist inference that essentially directly allows you to eliminate the problem of the normalization constant. And the suite of methods that I'm referring to is, of course, Stein's method. So you can use Stein's method, and because it only depends on the model likelihood via the derivative, you essentially get rid of, the log, the derivative of the log, you get rid of the normalization constant. And so if you use, for example, what is called the kernel-Stein discrepancy as your loss function, you can suddenly simplify graph models in particular quite substantially. And for one special case in this, we actually have an interesting special case. The paper isn't on arXiv yet, unfortunately, but it's in the last stages. So this will be coming online in the next month, hopefully. For one special case, when your likelihood model is actually, it's intractable. So the normalization constant is unknown, but it's part of the exponential family. This happens to be the case for lots of graph models, for example. So it's an exponential but intractable likelihood model. And you use a normal prior, we can actually show that the resulting generalized posterior has a closed form. So a problem that previously was doubly intractable can actually now be made available in closed form if you modify the original problem. So you've solved a fairly practical problem in that case. This is something from a machine learning application here. So here what we've done is looked at a problem called a deep Gaussian process, which is really, it's just a fancy name for saying you have a hierarchy of Gaussian processes. So the prior of your base Gaussian process again is a Gaussian process, and then you put another Gaussian process on top of that, and you hope that it helps you overcome some of the lack in expressivity of the Gaussian process. A problem with it in practice is obviously it's not very easy to compute, so you always need to approximate the resulting posterior. And another problem is actually that that the likelihood model you actually attach at the end of your very complicated hierarchy of priors is fairly simplistic. So usually you end up with a rather absurd situation where your prior is extremely expressive, but you're then squeezing it through a likelihood function that actually will be misspecified. And what happens here is you can actually show that when you treat this, once again, by using a loss function or a scoring rule that accounts for this misspecification inherent in how deep Gaussian processes are set up, you can actually massively improve the out-of-sample performance. So this is what's essentially shown here. So the blue dots are the method where we've replaced the standard Bayesian posterior, or the standard approximation to the Bayesian posterior, with an approximation to a generalized posterior. And the further to the left these points, the smaller the test error is. And this is over a range of different settings. So just to show that this is not an artifact of picking one particular setting and one particular data set. And you could show something similar for Bayesian neural networks. In this case, we are not worried about the likelihood model, but we're actually worried about the prior, like we were discussing earlier. So here, once again, you can essentially relax the influence of the prior on your posterior. So you can basically say, I want to weaken the regularization that the prior imposes on my problem. And once again, you can show, so the orange dot here is the baseline. So this is what people would compute in practice. In this case, the variational approximation to the Bayesian posterior. And to the left of that is a regularization term. In this case, it's the Renyi alpha divergence, but it's not important. It's essentially a weaker regularization of the prior. And what you can show is that consistently you will get a better test error on these methods if you just ignore the prior a bit more. What's encouraging for the Bayesians, of course, so you don't want to ignore all of the prior, otherwise why are you being Bayesian in the first place? What's encouraging for us Bayesians is that it actually curves back. So if you look at the shape of this curve, so I should note that it's not a coincidence that these are all banana shaped, because this point here has the strongest regularization. So here you're actually letting the prior influence the posterior even more than in the base case. This is the base case. And then the influence of the prior gets weaker and weaker. And what this tells you is, as it curves upwards, is that actually if you ignore the prior too much, you're then overfitting to the data. And so there's still a benefit to being Bayesian. And while the banana-shaped curve is not visible on these plots here, trust me, if you increase it further, it'll bend backwards and actually be doing worse. So that's good news. There is still a benefit from actually having prior beliefs in the first place, even if they're not perfect. Okay, and so in the last part, I kind of want to talk a bit more about some of the, so far I've talked mostly about methodology. I want to talk a bit more about some of the theory questions that I'm answering at the moment, or that I've looked at in the past. And one particular interesting behavior that I've looked at is asymptotics. So what happens as n goes to infinity? A collaborator of mine in Japan has actually recently found closed form solutions for these optimization problems in a very non-standard setting. So when your regularizer is an arbitrary F divergence rather than the Kovac-Glaber divergence, so you get sort of really weird and cool posteriors that are quite different from what you will have seen before. And also questions like, can we compute the dual form? Can we work with that? Very broadly speaking, so we've explored the applications or the methodology so far. There are two other areas of study, the statistical properties and the mathematical properties. And the way I'm distinguishing those is, when I say statistical properties, I specifically, what I'm interested in is things like what happens in the large data limit. Can I use those to reinterpret existing statistical methodology, et cetera, et cetera. Whereas the mathematical property really relates to properties of the optimization problem. So questions like, does the minimum exist? When does the minimum exist? Can I connect this infimum problem to a corresponding supremum dual problem, et cetera, et cetera. And I'm interested in both classes of questions, obviously. Now, one interesting note maybe before we go to some of the more technical points on this agenda is that you can actually motivate this entire generalization that we've sort of derived intuitively at the beginning. You can sort of motivate it axiomatically. And in particular, you actually only need two axioms. One of them says, I want to always be able to cast my optimization problem, to cast my posterior as an optimization problem, which trades off an in-sample loss against a deviation from the prior. So essentially, you see the optimization problem that underlies the Bayesian posterior, and you say, I always want that property. And then the second axiom you need is you want to say that I don't want the optimization problem itself. Oh, it's a bad way of expressing it. So basically, the moment you impose axiom 1, you effectively immediately can show that your posterior always needs to be the solution of an optimization problem of this form for some function f. But this function f itself may actually depend on your inputs at this point. So it may depend on the losses, it may depend on your prior, etc., etc. And then you're saying, well, in the standard Bayesian case, that's not the case. So I don't want f to depend on any of these things. And in fact, I want to recover the standard Bayesian posterior. And the moment you impose that second axiom, you immediately find that the only way that you can generalize Bayesian posteriors if they adhere to these two axioms is if you, in fact, recover the form that I presented you earlier. So just as a side note, that you can actually argue for this in a more formal manner. The second thing you can do with these optimization problems is you can reinterpret existing methods. So I was alluding to this earlier. When people speak about variational inference, they will often show you the picture that I've shown here on plot A on the left. So this picture, you have the Bayesian posterior, so that's Q star B. But your computational budget is limited. You can't actually work with this. So rather than doing Markov chain Monte Carlo sampling, because maybe you work in computer science and you don't know how it works, or maybe you actually think it is better for your particular problem to use variational inference, you have a set of probability distributions Q, and you're trying to find a distance measure between your Q star B and this set Q. And then according to this distance, it's not a real distance, it's not a metric or anything like that, but you use this distance measure and you minimize it to project the thing you actually want into the set of posteriors you can actually compute. And this is one way of understanding what variational inference does. And in fact, this has led to many methods where people have argued that it's maybe not good to project Q star B into the set using the Kullback-Leibler divergence. You may want to use divergence X. So for example, people have proposed to use the Rene divergence instead, the alpha divergence, or the reverse Kullback-Leibler divergence. And you can do all these things and still formulate your variational inference problem as a projection operation. What the formulation that I showed you earlier does, it reinterprets the existing problem and says, well, actually, you're just solving a constrained version of the original Bayesian problem. Yes, and with that in place, you can actually show that if what you care about really is the objective of the Bayesian posterior, then using any of these projective methods over the same set Q is always going to be suboptimal in the standard optimization sense. Though that's not necessarily something that is meaningful for practice. So I think I'll skip this part as well. Yes, you can look at consistency results or asymptotic results. So I mean, it's obviously well known that the standard Bayesian posterior converges. So the question becomes, under which conditions can I say something about this posterior that is only specified as the solution of an optimization problem? And you can actually show that under fairly minor regularity conditions, this Q star n will converge eventually to a Dirac measure at theta star. So if there exists a theta star which minimizes the expectation over the loss, so you're assuming that all your data are IID from P of X, and you define theta star as in this case, let's say it's the unique minimizer, as the unique minimizer from this expected loss, then as you get more and more data, you would want your prior to be ignored eventually. And you can effectively show that this holds under mild regularity conditions. What's much tougher is actually to show anything about the rate of this convergence. The reason for this, by the way, and also the reason why this theorem 1 is actually fairly difficult to establish, is that you're dealing with a sequence of optimization problems whose solution is not known in closed form. So what that means is you actually have to show that the objectives that you're minimizing over converge in a very strong sense. And the sense in which they converge is gamma convergence. So gamma convergence, very roughly speaking, it's similar to epi-convergence, or the convergence of the epigraphs of your functions. What it tells you is that if two functions gamma converge, then the sequence of their minimizers will also converge in a particular sense. And this is what you need to do for theorem 1. And it's also what you would have to do to establish a theorem 2 in full generality, so an asymptotic normality result for the Bayesian posterior. I haven't managed this part yet. This first part I have managed, but the second part it's an open question whether it's even possible. And maybe you could prove that in general this won't be the case unless the divergence is the Kullback-Leibler divergence, which would also be an interesting finding. Very roughly speaking, what do people know, what don't people know? If you only vary your loss function, and you stick with the Kullback-Leibler divergence and you optimize over the entire space of probability measures, then effectively you always get consistency. And if you get a nice enough Taylor expansion for your loss, you also get a Bernstein-von Mises theorem. If you vary only the space over which you optimize, so this is actually, there's a paper by Badruddin and Pierre Alquier that does this. And there's also a concurrent paper by David Bly, where they show that if you consider a variational subset here, then basically the same thing happens if your likelihood function is smooth enough and this set is large enough to contain the normals. Again, you will be asymptotically normal. If you vary both at once, it's basically the same story again. And if you vary L3, like I just said, you do get consistency. It's unclear if you get a Bernstein-von Mises theorem. Yeah, closed form. So this is pretty cool. Pretty exciting. This is not something that I was involved with, but I'm very happy about that this was found. We know that Gibbs posteriors are the closed form of the problem that I showed you earlier, when you use arbitrary loss functions and you still optimize regularizing with the Kullback-Leibler divergence and over the space of all probability measures, then the thing you get looks like this. And sort of an open question is what happens for other divergences. Does the minimum exist? The answer, by the way, for does the minimum exist? In general, yes. You need very, very, very small conditions on D. So this divergence D has to be lower semi-continuous in Q, so in the posterior argument, and it should be lower bounded, which if it's a divergence will be by 0. Okay, so usually they exist, but it's unclear whether they're usually unique. That's already more difficult to establish, and if they exist, what they actually look like. And Pierre Alquier from Riken in Japan, he showed that actually if you penalize with any phi or f divergence, you can actually get a closed form. And this depends on the Fenfield conjugate of the function f that you use within your f divergence. And this here, equation 3.4 doesn't look like it's useful in any way, but actually for two special cases of interest, I've extracted this from his paper to show you what this actually would look like in practice. If you use the chi-square divergence, for example, which is always a stronger regularizer than the Kullback-Leibler divergence, so you can actually upper bound the Kullback-Leibler divergence with this, you can actually show that the posterior looks like this. And if you pause for a second, you look at this posterior, what you'll notice is this very cool normalization constant, lambda t. So you know how in normal Bayesian inference, there's a normalization constant, but at least it's multiplicative. Here we have one, but it's not even multiplicative. So it's kind of nice because you can write down this sort of generalized posterior, but you can probably not compute it very easily. At least I don't see how at this point, because you would need to somehow estimate this lambda t, this normalization constant of the posterior, and it's interacting with the entire expression in a fairly complicated way. And you can generalize this for p-power divergences as well. So this is the form this generalized posterior takes if you penalize with a p-power with essentially the chi-p divergence, if you want. Another thing that recently, so this is unpublished as of yet, but as I was mentioning earlier, we could also consider what happens if we look at the dual problem of the infimum that we've been studying all the time. So if we look at whether this dual problem exists and whether it satisfies strong duality, you can actually show there are cases where this satisfies strong duality. And it's very insightful because what it tells you is that the divergence that you're specifying can effectively be reinterpreted in a particular sense to represent the budget of an adversary you play against. Let me explain this a bit. So if you look at the dual corresponding to this problem, what you will find is you are still trying to minimize some loss. So this g of pi here means you're trying inside the supremum to still minimize a loss over the set pi. But this true loss that you actually want to minimize in the original problem is being perturbed by some additional term h. And so this additional term h is what the adversary throws at you. So the adversary tries to make your loss bigger. So it tries to fool you into minimizing something you don't actually want to minimize. At the same time, though, the adversary pays for making your loss worse by modifying it with h, with this term here that I haven't written out because it's it depends on what d is exactly. But the important part here is the budget for h. So what the adversary pays for perturbing your loss will depend on the choice of d. And so in this way, you can actually reinterpret well, Bayesian inference itself, but also the generalizations as an adversarial game, where the budget of the adversary directly depends on how you regularize away from the prior. And this is sort of hidden in the notation, but obviously the prior actually serves as a, I would say, cost function. So the prior, if the prior is large on some space, then the adversary will pay more, quote unquote, to perturb the loss function in that area of high prior mass. Anyway, so this hopefully will be wrapped up in a paper soon as well. But yeah, I just wanted to give you like a short stroll of the kind of problems that we can look at if we look at things through the lens of this optimization problem. And so I think I'll wrap it up here as well. So just to summarize, I hope I managed to convey that sentiment. If you do Bayesian inference, there's one optimization problem you're solving. And this optimization problem is associated with at least 3 assumptions that may be violated in practice. And they're definitely often violated in the field I operate in a lot, which is machine learning. And there, it often makes sense to consider other problems that you can formulate within the same family of problems and solve those instead. And that has often has practical advantages. On the downside, we know much, much less about the theory of these objects because they haven't really been studied yet. But that's also a good thing because it means that there's more to do. And so if any of the things you heard today sound like they're interesting to you, please also feel free to get in touch and reach out. And I'll gladly point you to more things that I think are related or important. And with that, I think I'll stop. There are also some references here of some of the things I've talked about. I'm happy to send the slides over.